Good morning, everyone. I'd like to thank everyone for attending this morning's webinar. We're going to be talking about photonic crystal fiber sensors. My name is Scott Newman. I'm the project lead overseeing the OptiMode product. The presentation and the research underneath it was prepared by Ahmed, an optical scientist here with the OptiSystem team. So the overall outline for the presentation today is going to be photonic crystal fibers and their use as sensors. And what we're going to be doing is I'll give a brief overview of a couple different sensor designs. We'll discuss the OptiMode product and how that product is used to assess these kind of structures. And then we're going to go into detail on two specific designs. So photonic crystal fibers fall into two main classes, and those classes are characterized by how the propagation is managed. What I mean by that is in one class you have a high index core. So that's this one on the top of the screen here. The high index has a high index core and a low index surrounding area. That low index is achieved by patterning the structure and punching in air holes or etching in air holes, depending on how the structure is built. And the propagation operates under the same idea as a conventional optical fiber. The second class for photonic crystal fibers is the photonic band gap style of structure. And these ones typically have either a low index core or a hollow core. So you have a low index core and a higher index surrounding area. These should not operate under the same principles as a conventional fiber. They operate the confinement. The transverse confinement is achieved through the photonic band gap, so the stop band, and it's designed in that fashion. And these two different structures provide a high degree of configurability and allow tuning of modal dispersion and tweaking of the confinement, which supports a wide range of applications. These kind of applications can include sensors for chemical, environmental, or biomedical applications. They can involve nonlinear optics, endlessly single mode fibers, high power beam delivery, extreme dispersion values, or even particle trapping. On May 13th, we have another webinar scheduled that actually touches on the use of photonic crystal fibers in nonlinear optics. So in this slide, we have three examples of low index or hollow core photonic crystal fibers. So these particular structures rely on the stop band in order to provide the confinement and the operation. And you can see that there's a broad diversity in how the structure can be taken advantage of for sensing. So in the first design, the one here on the left, what we have is a photonic crystal fiber with a narrow, very small core air hole, and that's been lapped down in order to give a flat surface in which we deposit gold that can be deposited, and that gold layer provides the means for plasmonic modes between the photonic crystal fiber and the gold layer. And then any analyte that is put on top of the gold layer will actually change the plasmonic mode and therefore change the coupling between the fundamental core fiber mode and that plasmonic mode. The second design is a gas sensor, and this particular one operates, it's got a very large air core, hollow core, and the analyte can be infiltrated into a selection or any number of the air holes, providing different responses and behaviors. And the third design that I have up here on the board is a standard hollow core photonic crystal fiber, but the outer ring is actually infiltrated with a temperature sensitive fluid, and then select air holes have a gold coating on them. And again, as with the first design, the temperature dependence will change the plasmonic mode and affect the coupling between the plasmonic mode and the fiber core, and therefore we have a means of monitoring a change in that temperature. The two designs we're going to talk about later on in the presentation will be designs 1 and 3. And we'll get into the results and the operating mechanisms of these particular sensors. Before we get into that, what I'd like to do is I'd like to talk about the product that was used to calculate these. So within the OptiBPM and OptiFDTD products, we have a sub-product called OptiMode. And this product is a mode solving suite, which includes a number of mode solvers. But for the interest of right now, the mode solver that we use is the finite element method solver, and it's a vector base. And the advantage of this particular mode solver for these applications is that it makes use of an adaptable triangulation to form the computational mesh. And this triangulation is not uniform. It's able to adapt and change. You've got large triangles in some places, small triangles in other places, and it's able to conform to both refractive index contrasts as well as expected field distributions. The user can obviously tailor the results by establishing parameters for this mesh. So on the form here, we can see that user can tailor the minimum angle for the triangulars, minimum edge length, max edge length, and triangular area. So you can actually give the algorithm some guidance as to how the mesh is to be defined. And under advanced mesh settings, we also have the ability to tell it to consider the dielectric or not. And when it considers the dielectric, for example, where we go from one dielectric to another, or we have a particularly high dielectric in one spot, the mesh can pay more attention to that particular spot. And we'll see that later when we look at specific designs. Next slide. So as you can imagine, these particular structures are quite complex, and you're not going to want to necessarily sit down and redesign these every time you change parameters. One moment before I go further, I do see some people raising their hands for questions. We'll take questions at the end of the presentation, and once I've run through everything, and then we can come back and talk about certain things. As I was saying, these structures are very complex, and the complexity of these structures results in you're not wanting to have to manually change these things constantly. And the OptiMode product has two particular features that help with this. One of them is a scripting engine based on Visual Basic Script. This allows structures to be created and changed, as well as specific analysis to be requested of the simulator. So you can request specific profiles, specific waveguides. You can position those waveguides. It's how it works. The second thing that is available is parameterization of structural parameters. So what you can actually do is you can specify certain variables for certain geometries. In the case of photonic crystal fibers, a perfect example would be hole radiuses and lattice constants. And these can actually be just set as parameters. And then if you set up your script using those parameters, changing the parameters will automatically change the geometry of the problem. So it's very easy to do parameter sweeps, very easy to do structural variation testing, and it allows you to handle these more complicated structures quite easily. And to support that, one of the things that the OptiMode product will allow you to do is if you do have a design that maybe was done by hand and doesn't have script, you can have the product automatically generate the script that would create that structure. So you can use this as a means for learning the product. Obviously, with any optical numerical calculation, the question will become, how do we model different materials, particularly material dispersion? Within the OptiMode product, material dispersion is addressed through Sellmeier and Lorentz-Drude fitting algorithms. Specifically, the Lorentz-Drude materials, those allow users to specify either the Lorentz-Drude parameters, as we can see in the table here, or it will allow a user to import a known data set, and the product will do the fit for you and determine what the coefficients should be in order to give you the best fit. And here we have an example of a fit being done on a specific refractive index profile. When you're doing numerical simulations, another issue that has to be addressed is boundary conditions. There are two primary ones that need to be concerned about when you're dealing with the mode solver, particularly with the photonic crystal fibers. The first one is to have a absorbing boundary condition, or a PML. This allows the domain to be truncated with a lossy boundary, allowing the simulation domain to be reduced. It also allows the calculation of complex refractive indices for leaky modes. So this is used if you have a very, very large cladding. Your field doesn't go all the way out through the cladding. You want to truncate that down to focus on your domain of interest. The second boundary condition, and this one gets used quite frequently in photonic crystal fiber research, is the use of symmetric electric and magnetic walls. And what these symmetric walls allow you to do is to take advantage of the symmetry and only calculate one particular section, and that field can then be duplicated around when you're looking in your final analysis. So I can actually bring that up here. You can see that the particular structure under examination has a fourfold, it has more than that, but it has a fourfold symmetry. So we could take advantage of symmetric walls along the X and the Y directions to reduce the simulation domain down by a factor of 4. And the last thing I want to talk about in terms of the features of OptiMode is if you're chasing a specific mode, you actually have a good idea of what the modal index of the mode you're looking for is. There is settings within the product that allow you to specify the actual modal index you're looking for, and that will help fine-tune the search to focus on that particular region. Our first design for today, as I said before, will be actually this is design 3 from the previous slide, but it's the photonic crystal fiber temperature sensor. And this sensor consists of a hollow core fiber comprising of a hexagonal pattern of air holes. Lattice constant is 2 microns. That inner core is 1 micron in diameter, and then the inner ring is 1.2 microns and the outer ring is 1.6 microns. And you can see that there's blue rings around select holes in the outer ring. That blue layer is a 400 nanometer gold layer on the surface of the air core. And what is done is the outer ring is infiltrated with a temperature sensitive fluid, and the temperature changes the temperature changes the refractive index of this fluid, which then changes the core plasmon mode coupling. Specifically, it's going to change the dispersion of the plasmonic modes between the fluid and the gold, and between the silica and the gold. And those changes will impact how those modes couple to the core mode of the fiber. And those changes in the propagation loss resulting from the coupling can then be monitored, and you have a temperature-based sensor. I want to give an idea again. We showed this a bit earlier, but what we're looking at here is the triangulation. The structure did have the fourfold symmetry, so we could take full advantage of the X and the Y symmetric walls. And when we zoom in, you can actually see how the mesh is adapting to the refractive indices of the material. So for example, the temperature dependent fluid or in the air, the mesh is a bit coarser, but around boundaries or within that blue gold layer, the density of the mesh is actually quite large. And by large, I mean smaller triangles, higher number of triangles. So the way to analyze the behavior of the sensor starts with looking at the real and the imaginary parts of the modal effective index of the fundamental core mode. And the imaginary part of the effective index provides us with the loss, which is what's shown in the blue line. And what we see here is we see 3 loss peaks. These loss peaks correspond to the coupling of the core mode to the plasmonic modes at the gold liquid and gold silica interfaces. This can be illustrated by also taking a look at the effective index, calculating the effective index of the plasmonic modes, which is this next slide here. And the blue dashed black and green lines that we see coming slanting across, these are the effective indices of the plasmonic modes that exist between the gold and liquid and the 2 that exist between the gold and the silica interface. And what we see is that as the effective index of the plasmonic modes intersects the effective index of the fiber core mode, that's where we actually get our peaks. Therefore, the modes are coupling, therefore we're losing power from the core mode into these plasmonic modes. Just to touch on the accuracy of the calculations relative to the reference paper, what we see here is we've shown the effective indices at 3 locations, as well, 3 wavelength locations, as well as the wavelength of all 3 peaks. That's the first table is the effective indices, and then the second table provides us the peaks. And we see that the OptiMode product is providing results that are within very good agreement with the reference paper. I do want to comment, the reference paper doesn't actually specify the wavelength for their second peak. It is shown in their graphs. This value had to be extrapolated from the graphs, and that's why we've got the asterisks there. But the OptiMode product is in good agreement with the reference. And now the question becomes, how do we go about using this as a temperature sensor? I got ahead of myself here. I do want to show the modes at the different locations. So this figure up on the top left, we have the plasmonic mode that exists between the silica and the fluid. And then what we see with figures B and D, this is the core fiber mode that exists when there's resonant behavior. So you can actually see field along the gold interface. And figure C is simply the field distribution at a non-resonant wavelength. We chose one at 700 nanometers, which was kind of between the dominant peaks. Now what we're going to do is we'll talk about how to use this as a temperature sensor. And this particular design, what ends up happening is that there is a dependence on the loss peak locations to the temperature. And the reason for this is, as I said, as the temperature changes, the refractive index of the fluid changes, and this changes the coupling. And as we see in the graph, as we're showing here the first loss peak, the one that was originally at about 630 nanometers. And this one actually tracks as the temperature goes up. So we actually have a blue shift with temperature increase. And if we take a look at the definition of sensitivity, wavelength sensitivity, where we look at the shift of the loss peak relative to a change in temperature, we actually see 720 sensitivity of 720 picometers over the 25 to, actually, my apologies, that's the 0 to 75 region. And that is how this particular sensor will track temperature. We're going to move on now to the second sensor that we want to take a look at, which is actually a refractive index based sensor, or more specifically can be used for biochemical analysis. This one was generated with script layout. It's a similar overall photonic crystal fiber to the other one, except we've got the core is much smaller. It's a 0.4 micron air core, and in this case, all of the rings are 1.6 microns. We don't have difference between the rings, and again, we have our lattice constant of 2 microns. In addition, this particular photonic crystal fiber has been lapped down almost to the core, so it has a flat, and then there's a 40 nanometer layer of gold deposited on top, and then you can have your analyte on top of that. And if we take a look at our discretization, this particular structure had a twofold symmetry that we could take advantage of. So we put in a symmetry condition, and only half of the domain actually has to be calculated. And for those who are interested in testing out the OptiMode product later, these are the specifications that were used for this particular mesh. So there was some modifications done to specifically the angle and the edge lengths in order to get the resolution here. And zooming in, once again, we can see that the triangular mesh is adapting to the dielectric. So where we have really high dielectric values or particularly contrasts, you end up having a higher mesh density there, which is where you need the higher mesh density. Specifically, this was a very narrow gold layer and you wanted to make sure you had a significant resolution in there. The triangulation algorithm allows for that to happen. So this particular sensor has two different polarizations to the core sensor. This particular fiber, the way it's designed, has two modes, two polarization modes. One is a X polarized and the other one is the Y polarized. The X polarized is highly isolated. It's a low loss core confined mode. We have the amplitudes, the intensities plotted here at two different wavelengths for this particular polarization. And you can see that it's highly confined to the core of the fiber. It's not going to interact or couple with the plasmonic mode. So this one isn't of particular interest to us. What is of interest to us is the Y polarization. So this particular polarization will strongly couple to the surface plasmon polaridon, or the plasmonic mode that exists between the silica and the gold. And what we see is there is an anti-crossing at the phase matched wavelength, which is this spike right here, which corresponds to significant mode loss. And that mode loss is the result of the fiber core coupling to the plasmonic mode. To get a sense of what we're talking about in terms of those field distributions, we have 4 different fields plotted here. We'll see where these come from, the specific wavelengths for these in a moment. They were taken at 560 and 664 nanometers respectively. And we see that we end up getting symmetric and asymmetric modes at these different wavelengths. So at 560, we have a symmetric and an asymmetric, and then again at 664, we also have symmetric and asymmetric, and the change of them will correspond to that loss peak that we saw earlier, which is located at 664 nanometers. To give a better sense of what's happening, what we're going to do is we're going to take a look at that previous graph, but we're going to take a look at fields at the different wavelengths. And what we see here is that the effective indices of the symmetric, which is the upper modes, and the anti-symmetric modes, we can see it track as we approach the phase matching condition, which is located here, at which point the two overlap and match and then carry on. What we have here is this upper band corresponds to the plasmonic modes. As you can see, there's heavy dominance at this interface between the gold and analyte and gold and silica. And then down here, this is our fiber core mode and how it adapts as we shift towards the phase matching condition and start shifting away from it. Now, this particular sensor has a number of different ways of interrogating the analyte's refractive index. There's specifically 3 that can be examined here. So in the first way, as with the previous example, we can actually track the position of the loss peak. So as the effective index changes, we see the loss peak changes from 664 to roughly 700 nanometers due to a refractive index change in the analyte of 0.01. This causes a redshift of a total redshift of 33 nanometers, and based on the sensitivity calculation, it gives us a sensitivity of 3,300 nanometers per refractive index unit. The second scheme is to monitor the power at a fixed wavelength and look at the amplitude sensitivity at each of those wavelengths. So what we have here is at each wavelength, the amplitude sensitivity SA is calculated, and we see that at 700 nanometers, we can actually get a sensitivity of 135 per refractive index unit. So that's your max sensitivity operating at 700 nanometers. This sensor would run at that particular wavelength. The third and final scheme for measuring the temperature change, the refractive index change of this particular structure, is to monitor the phase difference between the X and Y polarizations. As stated before, the X polarization is not affected by the plasmon and therefore by the analyte. So by looking at the phase difference between the X and Y polarizations, we can actually track how much the Y polarization is being affected. And we can use this normalized expression down here on the bottom right to calculate that normalized phase difference and plot it based on the different refractive indices. And with this particular one, what we can see is that, again, the sensitivity at 700, roughly 700 nanometers, it's about 695 there, we can actually see a significant phase difference between the value calculated at 1.33, refractive index of the analyte of 1.33, relative to the phase calculated at the refractive index of 1.34. And this will actually provide a significant sensitivity to the calculation. Unfortunately, I do not have the precise numbers based on our results. I do know it's in the tens of thousands of degrees per refractive index unit per centimeter. The specific reference this design is based off of cited a value of just over 50,000 degrees per refractive index unit per centimeter. So there's 3 different ways of using this particular sensor and monitoring the refractive index change of the analyte. And as with both designs, it's relying on the the coupling between the plasmonic and the core modes. And that is going to bring us to the conclusion of the discussion of the designs. I do see a number of people have raised their hands with questions. I would like to request that for those of you who've raised your hands, if you could put the question into the chat so that I can read it and respond, we'll go ahead and do that. So just to touch down, I do see a number of people have indicated in the product they've raised their hand to ask a question. If you could type out your question in the chat window so that we can address any concerns you might have. I do see one person requesting that the slides be shared. That will definitely be done once the presentation is done. I do see a second question here addressing the integration of OptiBPM and OptiSystem together. There are a couple of different ways that integration can be done. The first way is OptiBPM can generate what are called scattering matrices or transmission matrices, and those transmission matrices can then be used within the OptiSystem product. And the second way that OptiBPM can be used in conjunction with OptiSystem is that OptiMode, which is part of OptiBPM, as we've seen in this product, can do calculations on fiber and calculate fiber parameters. And then those fiber parameters can be used within specific components within the OptiSystem product. Bear with me here. I'm just taking a look at questions. Presentation will be shared. We got another one here. So I do have another question here, and it's in relation to the second design we looked at, and it's what is the difference between looking at wavelength sensitivity and amplitude sensitivity? I'm assuming you mean difference in terms of how they're measured as opposed to the actual sensitivity itself. But obviously one of them we're tracking. So that's you're tracking the actual wavelength shift, and that's how the sensitivity is measured. Whereas the other one is specifically looking at the amplitude and the loss in that amplitude. So it depends on your application and how you'd want to measure it or what you want to measure. I would imagine, and I'm speculating on this one, I would imagine that the wavelength tracking might be a little less, little more tolerant to noise within an experimental application. But that's the fundamental difference between the two. Bear with me, I'm just trying to track through the other questions, make sure I didn't miss anybody. I do have somebody who's asking about whether you're looking for high or low sensitivity. Obviously, as a sensor, you want to increase your sensitivity as much as you can. Ideally, you want your structure to be as sensitive to whatever it is you're trying to measure as possible. Okay, I do have another question here in regards to the integration of the photonic crystal into the system software to design a complete system. As I did say with the other question related to this, the OptiMode product will calculate the fiber parameters, and those fiber parameters can actually be used within OptiSystem. If you bear with me for a moment here, I am going to open things up to one of the panelists here if he wishes to chime in on this. What we have here is Ahmed. He is the director of the OptiSystem product, and he should be able to answer that specific question if he wants to go ahead and address it here.
Okay, thanks, Scott. Actually, as you mentioned, the calculation of all the parameters of the photonic crystal fiber can be done in OptiMode, and you can import these parameters into the fiber component models in OptiSystem, and then you can do your analysis there. full system analysis there. And as mentioned earlier, on May 13th, I guess, there would be another webinar which we would talk basically about this feature of using OptiMode to calculate photonic crystal fiber parameters and then use them in OptiSystem to generate supercontinuum and study the effect of Raman self-frequency shift, which we had done using both software, OptiMode and OptiSystem, and it's verified experimentally with some references. So tune to that, please. Thanks, Scott.
No problem. I do have another question here. A couple of people actually are asking for links where they can download the OptiWave trial version for the simulation. So if you go to optiwave.com, along the top, you will see software and the download link. The two products that we're discussing today, the first one is the OptiSystem product, which a number of people are asking about. That one is there. If you're interested in getting the OptiMode product, you need to download the evaluation of either OptiBPM or OptiFDTD. The OptiMode is not a standalone product. It's actually offered within as a sub-product within those other two. But if you install those, it'll give you a 30-day evaluation of those products. And I do have a question on what version you have to use. Any of the latest versions of the product will have this support. So there's not a restriction necessarily on your version. Believe, just bear with me again for a moment as I check the questions. And again, I've got questions in regards to software availability. Obviously, as we stated, there's an evaluation copy of the product that's available on the website. It's good for 30 days. In terms of obviously premium or paid versions or student versions, I would urge you guys to reach out to our teams. The best one to use would be support@optiwave.com, and we can get you in touch with the appropriate technical team as well as sales team in order to sort out what solution is best for you in terms of pricing and product. I do have I think one final question here, and I've got two. I have somebody asking about FDTD mode. As I said before, OptiMode is a sub-product within OptiFDTD, so OptiFDTD is also set to use the OptiMode product. If what you're asking is, can mode solver be used in a finite difference scheme, we do have a finite difference mode solver that works perfectly well, but for these particular applications, because of the strength of the triangularization inherent to this particular FEM method, I would suggest using FEM for any kind of photonic crystal fiber analysis. And I believe that sums up all of the questions that I can see, at least. So what I'd like to do is once again thank everybody for their attendance and for joining us on the webinar. We will be making the slide deck available through the website. You'll also be able to, if you're registered for the webinar, which you're here, so you are, you'll be able to download this webinar to review on your own time. If you have any questions in regards to what we've done here today that I haven't addressed or my colleague hasn't addressed, please send an email to support@optiwave.com, and we can follow up with you and help you out with your questions or concerns. Once again, thank you very much for attending, and have a good day.